we talked about TPC, differential pulse code modulation. We said that have a wide sense stationary highly correlated x of n, then x of n can be written as so this hat shouldn't be here. So plus eta n and eta sigma eta square less than sigma x square, leading to compression. Right? This was the logic.
Yes, sir.
Yeah. So based on this, now the question is how to get eta n from xn. Right? How to get eta n from xn? So to answer that, we write eta n equal xn minus w Hermitian x. Right? Right? So if we can get this,
Hello?
yeah, BB.
Sir, can you explain that?
Sorry, yeah, Bhanu.
Can you explain that? How
Yes.
does it lead to compression?
How does it link to compression? You were there yesterday?
Yesterday it seemed like it is clear, but still there is a
Ah.
little confusion.
Okay. See, what we have is, so in general, so I'll just you started information theory, right?
Yes, sir.
Yes, sir.
Yes. So you know that so this might have been covered that for an event A, the information contained in A is minus log this is done.
Yes, sir.
Yeah. And the notion of entropy is there.
Yeah,
Yes, sir.
entropy is in the first class.
Yeah.
That's it.
So entropy is the average information in a source or average message in layman terms, right? This is measured in bits. Fine. And entropy of a continuous Gaussian random variable is this 2 shouldn't be there. Complex Gaussian. Fine. This I assume that this I'm not proving right now. Your information theory course, you will prove this maybe in a couple of weeks. So the entropy of a continuous Gaussian random variable is pi sigma square, or for accurately representing a Gaussian RV with variance sigma square, we need log to the base 2 bits. Fine. Manu,
Okay.
this logic makes some sense
Yes, sir.
because the information you know, or the information content in bits you know, is directly proportional to the variance or the uncertainty.
Yes, sir.
Since it's proportional to the uncertainty, it makes sense that and entropy is a measure, and variance for a Gaussian random variable is a measure of uncertainty, right?
So can you repeat that?
For a Gaussian random variable, variance is a measure of uncertainty. We agree
Okay,
on
sir.
that.
Yes, sir. Yes, sir.
So because of that, just a second. Yeah. Because of that, the variance is a measure of the uncertainty, and consequently, the more the variance, the more bits we will require to represent that random variable, right?
Yes, sir.
This is not an exact mathematical description. This you will understand once you cover enough information theory. This is just an intuitive explanation for it. That. So
Okay.
the smaller the variance, the less number of bits we will require to to represent that random variable
Yes, sir.
with the equal fidelity. There is something called rate distortion that I am skipping, or that I'm not going into right now. But the general intuition is that the smaller the variance, the lesser number of bits you will require to represent that random variable, and therefore this works. Fine.
Okay, sir. Yes, sir.
So now to get eta, we need to get.
So could you repeat the last sentence once again? Final.
So the larger the entropy, the more will be the number of, the larger the variance, the larger will be entropy. And the larger the entropy, the more information that has. So we will need more number of bits to represent that.
Okay, so here this relation, like variance of eta and like how does this leads to compression, sir? Leading to
So
just
see, if you try to represent x, if you try to represent each sample of xn, each sample of xn has a larger variance. So you need to describe each sample of xn using a larger number of bits.
okay.
Right? So suppose you have an image. You take samples of an audio file. We'll stick to audio for now. And you say you have to represent each sample using 8 bits. So 1 byte per sample,
Yes, sir.
8,000 bytes per second.
Okay.
So you are So 1 second of audio file is 8 kilobytes.
Yes, sir. Yeah.
And 1 minute of audio is how much?
16 to
16 to 8, 480 kilobytes.
yeah.
Fine. At the same time, now consider that you can represent you via good compression. This eta has a small variance. You only need to represent eta. Then you can represent eta using 2 or 3 bits, say 3 bits. So instead of 8 kilobytes per second, you get 3 kilobytes per second.
Okay, sir. Yeah, got it. Fine.
And 3 kilobytes per second means the 480 kilobytes per minute gets reduced to 18 kilobytes per minute.
Yes, sir. Got it.
Compression.
Yeah, got it.
Fine.
Thanks.
So
Yes.
there is an exercise on. So in your lab sheet, there is an exercise on Jpeg compression. You know Jpeg? You guys know
Yes,
Jpeg? Yeah.
Yes,
So in your lab sheets, there will be an exercise on Jpeg image compression. So you can get a hang of things once you do that. So now to get eta, we need to get x hat n, right? And to get x hat n, need w, right? So, and at the same time, we want that the variance of eta should be what? Minimum possible to get the best compression out of it.
Yes, sir.
Yes, so we want the variance of eta to be minimum. So the problem that we have at hand is we have to find these weights such that the variance of eta is minimized. Agreed?
Okay.
yes, sir.
Fine. So we have this. So what do we have? We have past data. What do we want? We want x hat n, and in effect, we want eta n equals xn minus x hat n. So eta I can also call prediction error. I can call it as prediction error.
yes, sir.
So what do we have? Past data. What do we want? X hat n. That minimizes the error. How do we get this? We get this ugly expression. That W equals min so we choose the set of weights that minimizes the error variance or minimizes the variance of eta. Fine?
Sir,
Yes, sir.
yeah, sir, I have a
Yes.
doubt. But sir,
Yes.
like we cannot shouldn't the variance of eta should be something like which is something like kind of inherent thing of the system. Like if we are
Yes.
considering
So
a sequential data
yeah,
of point process.
yeah. So the variance of eta is inherent,
Yeah.
but
So
we
like
don't
how,
know the weights.
but with different weights, you are saying the variance of eta will change. That's why we are minimizing it, right?
Yes, minimum possible.
But like shouldn't the variance of eta be constant for everything? Like just like
See,
I'm kind of confused.
you eta is unknown right now. You
Yeah.
have to obtain eta.
Okay.
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 So, and the eta will depend on the estimate. So,
But like okay, like we have to obtain eta. I get that. But the
yes,
thing is like shouldn't from all possible routes the eta should be same?
yes. The optimal eta should be the same.
Okay.
There is only one optimal eta.
Okay.
We will do some mathematics to get to that.
Okay.
Okay. So
Okay.
just have some patience and you will get to know what I am talking about. Fine. So let's say sigma eta square equals expectation of xn minus x hat n whole square, right? We agree on this?
Yes, sir.
Yes, sir.
Yes. So equals expectation of xn minus summation. I'll use the vector notation later because that becomes confusing. So I will derive everything in the vector notation as well. But let's first do it in terms of the summation. K equal to 1 to P WK conjugate X n minus P. Fine. We get this beast
Yes, sir.
from yesterday? Yes. Now this equals expectation of xn square plus summation. So summation and expectation are both linear operations. So I'm skipping a step and moving the expectation inside summation. Summation. So since this will be the square of a summation, it will be a double summation. So k equal to 1 to p, L equal to 1 to p, wk wl expectation of x n minus k x conjugate n minus l. We did this yesterday. This thing we had we had calculated yesterday. So this is same as that minus summation k equal to 1 to p wk conjugate xn xn minus p xn conjugate minus summation k equal to 1 to p wk xn xn minus p conjugate. Fine. These beasts. Sorry, there should be an expectation over here. An expectation here and an expectation here.
So isn't that xn minus k?
Xn minus k, yes, sorry. My bad. Now are these okay?
Yes, sir.
Yeah. So now I simply write the expectations out. Sigma x square plus summation k goes from 1 to p, summation L goes from 1 to p, wk conjugate wl r L minus k minus summation k goes from 1 to p, wk conjugate wk conjugate rk my wk conjugate rk minus rk conjugate wk. Fine.
Sir,
Yeah, Kirti.
wk is a vector or scalar here?
Scalars.
Okay, fine.
Wk's are scalars. W, we'll define the vector. We had defined the vector W yesterday. We'll define it again.
Okay, sir.
Okay. So this. So
Sir, can you move
now,
up just a bit?
yes.
Okay, sir. Okay.
Okay. So now,
Sir,
yes.
isn't it R of minus k, WK
R
conjugate?
conjugate. R of
No.
k. So
As the
yes.
convention is
Yes.
L
Yes.
minus
Yes.
k.
Yes. 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 R of minus R wk R conjugate k. And yes. So this is because I am used to the vector notation, and just give my pen a while.
It's WSS, right? So R of minus k should be same as R
No,
of.
no. R of minus k would be R of R conjugate of k, which is what I'm going to write. R conjugate k. So this is because in the vector notation we define the vector as R conjugate. So that doesn't lead to a problem. So this Vignesh, is this now is this right now?
Yes, sir.
Yes. So R of minus k equals R conjugate k. That's why. Fine. So now we have sigma eta square as sigma x square plus summation k equal to 1 to p, summation L equal to 1 to p, wk conjugate wl r L minus k minus twice real part of k r k summation. this eraser causes trouble, so I'll write it like this. Twice of real part of wk r k summation, I forgot again, k equal to 1 to p. Fine.
So should it be plus now then?
Where?
Because
No,
it is
minus.
conjugate minus real, like conjugate minus the normal one. So it should be minus into 2 real. Already there is
So
minus.
this is plus. This is plus.
Okay.
This is plus inside the bracket. That because of the too much overwriting there, this look like a minus. Fine. And conjugate minus original will be minus of imaginary, not real. Kirti, is this okay now?
Yes, yes.
So now we want to find WKs that minimize sigma eta square. Fine. So how do we do that?
Differentiate.
Differentiate, yes. Also, for complex, we covered this in last semester. Did we cover this? Did we cover this in last semester?
No.
Okay. And this is how we define the derivative with respect to a complex variable. So del z by del z equals half, assuming that x and y are independent variables. Half del x plus jy divided by del x minus j del x plus jy del y. Fine. So half. So del x by del x 1 plus j0 minus j times 0 plus j equals half into 2 equals 1. Fine. Similarly,
Yes,
this is the tricky part, or this is the non-intuitive part. Del z conjugate by del z equals half jy del x minus del y x minus jy equals half 1 minus minus plus minus plus and plus j times j equals 0. Fine. So if the real and imaginary part of a complex number are independent variables, then the complex variable and its complex conjugate are two other independent variables.
Sir, is it like kind of that intuitive, like conjugate and the number itself are perpendicular?
Yeah,
In a
kind of
plane.
that. Yeah. Kind of that. Just a second. I'm getting a call on the landline. Just it's important. Yeah. Hello? Yes. Sorry, that was from the department, so I had to take that. So this is fine now. So the fun part is that now if I differentiate with respect to WK conjugate, WK will disappear, and if I differentiate with respect to WK, WK conjugate will disappear. Right? We agree on that? Am I audible?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
So do we agree on that? If I differentiate this with respect to the number itself, the conjugate will disappear. Or if I differentiate with respect to the conjugate, the number itself will disappear. The random variable itself will disappear. No, the variable itself will disappear, not the random
Yes,
variable.
sir.
Yes, sir.
Yes, sir.
Yes, great. So del by del WK conjugate sigma eta square equals. So the first term is directly 0, constant. Fine. The second term is, or I should look at this one, the longer version. Yeah. The second term is WL RL minus K summation L goes from 1 to P minus. Now these two terms, W conjugate term will stay and the W term will go to 0. So minus RK. Fine. And from the little differentiation I know, or from the little mathematics I know, we know that del sigma eta square by del WK conjugate should be 0 for all K. Right?
How, sir?
Huh?
How?
We differentiate. So how do we optimize in terms of when we have multiple variables? Or how do we find the minima and maxima when we have multiple variables? The condition is that when we have multiple variables, the derivative should be 0 for each of those variables for a minimum or maximum.
Yeah.
Right? Or in this case, what it becomes is this is the derivative. This I leave out as an exercise. Shouldn't be hard. If it's hard, if it seems hard, I can possibly do it in some lab session for you. But right now I'm leaving out this derivative as an exercise. So,
So you're
yeah, Bhavji.
differentiating with respect to one number K. How are all of the K's getting like vanishing?
Yes,
Oh.
sir.
Yes, so W1 W2 are among themselves independent. So del W1 by del W2 fine.
Yes, sir.
Oh, all right. Okay.
So this, so in general, K R K goes from 1 to P. Sorry, L goes from 1 to P equal to R of K. Make sense from this equation? So if this is equal to 0, then I can say that this is true.
Yes, sir.
Fine, great. So now in order to solve for WKs, I simply need to solve this equation, solve these equations. So there are K unknowns, W1, so there are P unknowns, sorry. P unknowns, W1 to WP, and P equations for K equal to 1 to P. So if we solve this set of simultaneous equations, we should be happy. Now the question is, how do we solve these simultaneous equations? So for the first things first, let's have a formal name for these. So these are called Euler-Walker equations. So these equations known as Euler-Walker equations, how do we solve these? To answer that question, let's write things in vector notation. So writing things in vector notation, I get x of n equals W Hermitian, sorry.
So, in the summation,
Yeah,
is that K or L?
this is L.
Like in the
The kth element
so from
summed over K, summed over L.
L from 1 to P, right?
Yes,
Okay.
fine. So if I write things in vector notation, we started from here. Eta n equals xn minus W Hermitian, right?
Yes.
And this equals sigma x square. This we know, minus W Hermitian expectation of xn plus, sorry, this should be plus, this should be minus, minus W Hermitian expectation of xn minus 1 x conjugate n minus expectation of xn x Hermitian n minus 1 w. Fine. This is fine.
Sir,
Yeah.
sir, won't there be a W in the second term?
Yes, there would be a w in the second term. Yes. Now fine.
So why not it's n minus 1, so x of n minus 1?
Sir, sorry. Yeah, it
X.
should be x of n minus 1. It should be x of n minus 1. My bad. So yeah, this is the problem with such derivations. That while we write these out, we tend to make mistakes. And this was one major complaint in your last semester's feedback. I know. I'm trying to improve. Yeah.
Sir, but you told yesterday that this n minus 1 and n wouldn't matter because it's White's.
Yeah, this is White's stationary, so it won't matter. But just for correctness, right now it should be n minus 1.
Okay.
It won't matter. That I will say again. So had this been a written exam, you would have done this. I won't have minded at all.
So for notation purpose, we can use this way, right? Because
yes. Yeah, for notation, but let it be for correctness, or for it's right, but it's not irrefutable, or it's not questionable. If I write it n minus 1, it's unquestionable.
okay, sir.
Okay, so this beast. Now let us define one more vector p.
Sir.
Yeah.
In one place you've written Hermitian, in another place you've written conjugate.
See, one is in the first one, the underlined one is the vector.
Okay.
And the thing that is not underlined is the scalar.
Okay, sir.
So let us define another vector to make our lives harder. P as I define this vector P as R1 conjugate to R. No, P is something else. So let's call this Q. RP. So I define this vector as R1 conjugate to RP conjugate. Fine?
Yes, sir.
So sigma eta square becomes sigma x square plus W Hermitian RW, R we had defined yesterday, minus Q Hermitian W minus W Hermitian Q. Fine? Fine. I can write this, write those summations compactly.
Yes.
Now, you have done that electromagnetics course.
Sir, what
Just,
topic that?
What topic?
Vector calculus.
Yes, sir.
Yes, sir.
You know what is a gradient, you know what is a divergence, you know what is curl.
Yes.
Yes, sir.
Yes, sir.
What is a gradient? I have a field function. How do I define its gradient?
The direction in which the rate of change of magnitude is maximum.
Yes, sir. Or like basically it shows whether we have a source or a
gradient. physical definition of gradient, or how is the gradient defined in terms of the del operator?
You just differentiate the vector, like all of its components individually.
Yes, all of the components individually. So you take a vector, you take a scalar, take its gradient, and the gradient will be a vector. Right?
Yes. Yes.
So now I have to find the optimal vector W. Right? So the condition for optimal W is gradient. This operation is also called gradient of W, or gradient of sigma eta square with respect to W is zero vector, where gradient of W, or gradient with respect to W, is del by del W1, or this to del by del W, or W conjugate, del by del W P conjugate. This is how I define the gradient of a scalar for vectors. Makes physical sense?
Yes, sir.
Yes. So gradient of sigma eta square with respect to W equals 0 plus. Now W Hermitian, since I take W with respect to W conjugate, so this W Hermitian goes to 1 and RW remains. RW minus.
Sir, can you explain just a bit of a math behind that differentiating W Hermitian with respect to W conjugate?
Just a second, another phone call. I'm sorry.
Okay, okay.
Yeah, sorry. So some student has, yeah. So one of your seniors is in trouble. That's the only point. Anyway, so
yes, sir.
I won't say more. Yeah.
Yeah. So can you explain just a bit of math behind differentiating that W Hermitian matrix with respect to W conjugate?
Yes. So see, W Hermitian, this is a scalar. For starters, W Hermitian RW is a scalar. This is a scalar. Fine.
Sir, W Hermitian is not a scalar. RW with like
W Hermitian RW is a scalar.
Yeah, W Hermitian RW is a scalar.
Yes. So the math would be this is, or rather, there's not much math. What is there is that I wrote this. Okay, so that for some reason. So this Euler equations. If I go to the scalar form of Euler equations, those somehow conveniently disappeared. You remember that we had just derived the scalar form of Euler equations?
Yeah.
I'll rewrite those. So
okay, so not an issue. Like I will try proving it, and if
no.
it does not work, I
So
will ask you again.
what I am doing is that I'll write the scalar form of Euler equations, and maybe when this misbehaves slightly less. So this, okay. So what I will do is this. So we are stuck anyway. So yes, so now what I'm doing is I'm just simply writing the scalar form of or yes, now it's yeah, here it is. So basically the Euler equations are summation L goes from 1 to P W L R of L minus K minus R of K equal to 0.
So that W conjugate and W Hermitian the same thing?
W conjugate and W Hermitian are the or W Hermitian is the vectorized version of W conjugate.
So, sir, when you're differentiate, I mean, when you're taking the grad with respect to W conjugate,
W
it
will
is already
remain.
a okay.
W will remain because W and we just proved that W and W conjugate are independent.
Sir,
Yeah.
just one doubt. When you're taking gradient of W conjugate bar, shouldn't it be W Hermitian? Because W is the vector. This lower
See,
bar.
W is a vector, W is a column vector. The gradient is a column vector. W Hermitian is a row vector.
Okay.
So, see, you can take the conjugate of a vector, which is fine. You can take the transpose. Hermitian is the conjugate transpose.
Okay, sir. So just got confused with the.
Yeah, it's perfectly fine. It took me 1 week to digest all of this when I studied this first. So it's perfectly fine. You're quite fast, actually. So anyway, so these two equations are equivalent. Q conjugate or so these two equations are equivalent. So I stack all of these equations, I get this. So in a way, I know that R equals R0, R1, RP, R conjugate 1, RP minus 1, and so on. And the kth row of R is Rk minus, sorry, R1 minus K, 2 R one minus K minus 1. Yes. Sorry, just a second. The kth row, because of 0. Yeah. R of two this. The kth row of R is this.
Yes, sir.
So if I multiply the kth row of R with Q, I get this. Sorry, I multiply the kth row of R with W, I get this thing.
Sir,
Yeah.
the first term, if it is r 1 minus k minus 1, won't the kth term be r of minus k alone? But it should be r of minus k minus 1, right?
Yeah. So okay, I'm missing something. So actually, this I'm messing this up.
Shouldn't it be +1 instead of -1 at the end?
And Manish, wait a second. I'm in trying to make this simple. I actually made it complicated. So we are also slightly kind of out of time. So let us pick things up at this point on Tuesday. If you don't have a
Okay, sir.
class.
Yeah, sure, sir. Not an issue.
So let's stop here, and we
Can you
will
distribute
pick this.
the notes?
Yeah, I will distribute the notes, and we will
Okay.
pick this up. Yeah, you actually asked a nice question. I never looked at it this way. Anyway, so we will stop here and continue on Tuesday.
Bye, sir.
Bye.
Sir.
Bye, sir.
Bye, sir.
Yeah.
Bye, sir.
Bye.